In this video, we look at triple integrals, but we focus on the aspect of them that I think is the most challenging, and that is focusing on the region. Sorry here. Let's focus on the region of integration. Okay, so what we can see in this problem is that we're given a triple integral. We're given the function 1 to integrate. We're integrating dv, and we're integrating over some region or domain in three-dimensional space. And the order for the volume element dz, dx, dy has been given to us. And so we can see here that if we wanted to sketch the region of integration, all right, we can see that z has to be bigger than 0, but z is less than 2x plus y. And 2x plus y, we know and recognize that as being the equation of a plane. Right? But then we can also see that our next limits, we have x being bigger than negative square root of 4 minus y squared, but x is also less than the square root of 4 minus y squared. And we'll come to recognize these square roots pretty quickly. We can see that if we square both sides of these equations, that you'll get x squared 4 minus y squared, and then that leads to x squared plus y squared is equal to 4. So we can see from these limits of integration in the x direction that we're going from x on the left, and that part of where on the left is a circle of radius 2. Sorry, let me make the radius there 2. And then on the right, which is the positive branch, okay, so putting them together, we had x squared plus y squared is equal to 4. And we can see from the last limit, we can tell what part of the circle we are integrating over, and that is y going from 0 up to y is equal to 2. So we have to be bigger than 0 in the x, but less than 2, but we also have to be, sorry, this is y bigger than 0, y less than 2, so we have to be bigger than y equals 0, but less than 2, and we have to have a circle on our left and right. So this was our region of integration in the xy plane, but we can also tell that we have a z entry. So if we're just going to sketch this region of integration that we are finding the volume of this region D, that region is going to look like, let's see, in the xy plane, right? X is going from a circle on one side, y is bigger than 0 but less than 2, so we're having a circle right here in the xy plane. But because we had z going from 0, z-axis, z going from 0 up to a plane, right, that we can tell that just a general sketch of what we're looking at is some sort of volume of a region with a slanty top. And the base of that region is going to be some sort of semicircle. Okay? So this is important because not always will the limits of integration be given to you. Sometimes you'll have to do this problem in reverse. You'll be given the region and then you're going to have to figure out the limits of integration. Okay? So if you want a nice picture about what this looks like, we can see here that this is part of the region. Okay. This is part of the region. Let me see. Let me pause for a second because it's looking like a quarter of a circle. So I'm checking my limits of integration here. Y is bigger than 0 but less than 2. Oh, and I can see that I plotted it only from x going from 0 to 2. So if we plotted this from -2 to 2, we would see a semicircular region with a slanty top, as we're seeing here. Okay. So another problem to look at would be to sketch, and we'll check our plot with this one in a second, but again we're finding the volume of some region D, and that region D has z bigger than 0, but z is also less than the square root of 9 minus x squared. So that's a fancy way of saying that x squared plus z squared is equal to 9, and that's for any value of y. Okay, so I think what we're seeing here is x squared plus y squared is equal to 9 is the equation of a cylinder. Okay, so here's the xz plane, and for any value of y, you pick your favorite value of y, we're going to get a circle of 1, 2, 3, 1, 2, 3 radius, and then 3 in the vertical direction. So we're going to get a circle of that radius for every plane y. Right? And so if we move over here to another value of y, we're also going to get a circle. And if we put all those circles together, we're going to have the equation of a cylinder that's kind of sitting on its side. So it looks like we're going from 0, z equals 0, up to that cylinder. So here's the z equals 0 plane. So we're going from z is equal to 0 in this plane up to the cylinder. Okay. What we don't know is what part of the xy plane we're going to be over. Okay, so now we start focusing on the y's. Y is bigger than 0, and we've seen the square root of 9 minus x squared before. That says that y is equal to the square root of 9 minus x squared, so x squared plus y squared is equal to 9. But y had to be bigger than 0. So we can tell that x squared plus y squared equal 9. In the xy plane, we're going to have a circle of radius 3 again. But x is going to go from 0 up to 3. So we're only integrating over a part of the xy plane, and so a little quarter of a circle, but then we also need to be integrating from over those values of x and y up to the cylinder. So we're going to have some sort of, it's kind of hard to draw this, but a circular part, a quarter of a circle part of a cylinder. Okay? So one could compute that integral. Evaluating the integral is not usually too big of a challenge, but it's the region plot, getting an idea of what it is that you computed. So if we look at this region plot and we go from z equals 0, bigger than 0 but less than the cylinder square root of 9 minus x squared, we can take a look at this, and y has to be bigger than 0 but also less than square root of 9 minus x squared, and x has to be bigger than 0 but also less than 3. Okay. And we want to integrate from x going from 0 up to 3. Let's just take a look at this thing over a maybe y going from 0 up to 3. Let's integrate it. Let's look at a cube, and let's look at all the values in the cube that satisfy the inequalities given. And let's let z go from 0 up to 3. 0 up to 3. Okay, and we should see, let's plot some more points. Plot points goes to 30. So kind of as promised, in the xy plane we're seeing a semicircle, but then from the top we're also seeing that we're looking at part of a cylinder. Okay, let me put the other plot in so you can see it. Here's P2, and if we've looked at all the other contour plot 3D, we had also the cylinder x squared plus y, I'm sorry, x squared plus z squared equal to 9. And let's plot this over the same region, and you should see where the cylinder is coming in, and you'll see where our region fits in that context. Okay, so let's show these two plots together. Okay, let's make it contour style. Let's make it blue, and let's make the opacity. Let's make it so you can actually see through it. All right, so there we are. There's our cylinder, and we are looking at the volume below the cylinder but above that semicircular region. And so we can see that this orange region fits right nicely inside of that cylinder, the blue region. Okay. And maybe we even extend z from -3. Why going from -3? Okay, sorry, -3. All right, but there you have it. So there's our cylinder, and we have the little region fitting in nicely with that cylinder. Okay, so ends the setup of a sketching the region of integration from the limits of a triple integral that had been given.